All right, section 3, we're going to look at what we call the binomial distribution and the geometric distribution. Now, what they are, again, are examples of our random variables we just finished up with. So again, random variables are random variable of interest takes on numeric values such as a count again, okay, which again was a discrete situation, or measures, which again would be a continuous situation. So there's some examples on the intro, page 382, and one of them they talk about is testing to see if someone has ESP. Okay, and so what it is, they talk about having 4 cards, each with a different shape on it. You're going to draw a card, and when you draw that card, you're not going to look at it, then you're going to guess what shape is on it. Okay, and then I'm going to keep track of how many times you get it correct. And then what we'll do is we'll put it back in, shuffle them up, and we'll do the same thing over and over again until we reach 50 tries. And what I'll do is I'll keep track of how many you get right. Okay? So this is going to be an example of what we call a binomial setting. Okay? Remember the idea? Binomial is prefixed for 2. So when we talk about the binomial setting, what we're looking at is either we have a success or a failure. We get 2 outcomes. Okay? So either you guessed what was on that card correctly or you didn't. Now another thing we need to do is make sure each trial is independent from the previous one. That's why we put the cards back in and shuffle them up. And then what we want to have is a set number of trials. And we call that n. Okay? And so again, we said we were going to do it 50 times. And then the last thing we look for is what's my probability of success, and we call that p. Now how we remember when we check to see if it's a binomial distribution, we use the idea of bins or binds. Okay, if you want to talk about that way, remember binomial. We check these 4 things first, and then if we do decide we have a binomial situation, then we will go forward with some other ideas. Now, if you remember, we can notate a normal distribution with a capital N, and then the ordered pair with my mean and standard deviation. We're going to do the same thing for binomial, except we'll use B, and then my ordered pair will contain N, my number of observations, and P, my probability of success. Okay, so here's another example. Once in a while, I'll get some people. If I play the lottery every week for a year, is this going to be a binomial setting? So again, what we want to check is that Venn idea. And when we talk about it again, B stands for success, failure. Well, success here is that I win. Failure is that I don't win. Each week is independent of the other week. If I won one week, I could win the next week again. Not likely, but I could. Number of trials, well, in a week, or in a year, there's 52 weeks, so I'd be playing 52 times, my probability of success. Well, that depends on our lottery. Okay, and so since they don't specify what the lottery is, we know if I'm playing the same lottery, my probability of success will be the same. It's a pick 3. There's 10 times 10 times 10, 1,000 outcomes. So my probability that my guess is correct is 1 out of 1,000. The same thing next week. Okay, if it's a Powerball, obviously a little different, but still 1 out of all my possible outcomes. So here's your definition of binomial random variable. Okay, probability distribution. Again, that's your table. It's a binomial distribution with parameters n and p, where n is the number of trials, okay, and p is probability of success. Possible values are whole numbers from 0 to n. So what they're saying here, when I build my probability distribution, x is going to equal my number of successes. Okay. I could have no successes, so that's why we're going to start with 0. I could have 1 success. I could have 2 successes, all the way up to n. This means every trial was a success. So in the idea of the ESP, all 50 of my guesses were correct. And then because we're making this distribution, again, 2 things. All my probabilities in this distribution are going to be between 0 and 1 inclusive, and they will add to 1. So we still want to check that situation. So an example we can look at now, how am I going to find these probabilities? So we have a situation here, we have a family, and the probability that a child has type O blood is 0.25. Okay? So if I have a family with 5 kids, what's the probability that 2 of them have type O blood? Okay? Okay, so again, if I want to go through and do this correctly, I should check my bins idea. Okay. So either they have O or they don't have O. Okay. Each kid's independent. I believe they say it in there. Yeah, right there, independently. So that's a check. You're looking at 5 kids. Your probability of success is 0.25. Okay, so now, one of the mistakes that happens is they'll say, okay, well, the first kid has type O, second kid has type O, third doesn't, so 1 minus, fourth doesn't, fifth doesn't. Now, what they're getting at down here is the idea of, well, which 2 kids have type O blood? Okay, so, was it the first and the second, or was it the first and the third, and so on and so forth? And what you see is there's 10 different ways to deal with that. And so what they do is they kind of calculate, there's 10 different ways we can have 2 of the 5 kids have type O blood. And just like we had up there, 0.25 times 0.25, that's where they're getting this 0.25 squared. And then the 7.5 to the third. Now, where this 10 is coming from, you may remember from an earlier course, is when we're talking about combinations. Okay. How we calculate combinations. This is how it's represented in the book. This is how a lot of times you've seen it. N, choose K. On your calculator, it's going to be an R, but same thing. What it says is if I have 5 kids, I need to choose 2 of them. How many ways can I do that? Now, we're not going to get worried about actually going through and doing this. We're going to have the calculator come up with a lot of these numbers, but that's the idea to remember the combinations. This is the big one that you need to know. How we actually calculate this probability out. We're going to compare it to what we just saw. So, the probability that the number of kids that have type O is 2. You can write it this way, or you can do the 5, choose 2. Now, P again is your probability of success. Well, here my probability of success was 0.25. This is the number of successes I want. Okay. So that's why we're saying I'm going to take that probability of success to whatever power. The number of successes, 0.25 times 0.25. Again, that's why we have to have independence, so I can multiply those probabilities. This is your probability of failure. Some books call it Q, okay, but we're going to do 1 minus P here. So the 0.75, well, N, that was my total number of kids minus my number of successes. So basically, that's saying is your number of failures here. Now, with your calculator, okay, we don't necessarily have to go through and use the formula to get my combinations. If I go math over to probability, you'll see the NCR number 3. Now, to do this, we first have to enter how many we're choosing from, and then we can go math over to probability. Oops, I need number 3, sorry. Okay. And then we need to choose 2 of them, and there's where they get that 10. And so then what we would do is write down that 10. Now to match up with the probability they had on the previous slide, I take that times my 0.25 squared times my 0.75 raised to the third. And we get the same value. So what's the probability of exactly 3? Well, that means probability that X, my random variable X, which talks about the number of kids with type O, is 3. Okay. So I have 5 kids, I need to choose 3 of them. Probability of success is 0.25. I want 3 successes. Failure is 0.75. I want 2 successes. Or 2 of those. Okay. Now, should we be surprised at more than 3? Well, what we're doing is looking for the probability that X is greater than 3. So what I'm looking for is the probability that X is 4, or, so we're going to add the probability that X is 5. You can add again because those can add at the same time, mutually exclusive. I'm going to go through and type that into the calculator, but you can practice that, go back a slide or 2 to see that. Another way we can deal with it in terms of the calculator, okay, is we have a feature, binomial PDF. PDF, probability distribution function, finds an exact value. Now, we use normal CDF when we're doing z-scores because we're doing cumulative. We want to add up a bunch of them. This is a specific one. So I did the probability x equals 2 on that last example, just so we know what the answer is. Okay? What I want to do is go to by binomial PDF. Same place we found normal. Second bars. Now, there's a whole bunch of them here. We don't want to have to scroll down every time, so we're going to scroll down here so you can see where it's at. It's in letter A. Okay? So letter A is your binomial PDF. And so, all I really need to do is, since I want A, I hit the alpha button, and then find my A, which is the math button, and it'll bring it up. Now again, notice your parentheses, means we have to punch some stuff in. So what I want to put in this case, is N, P, and then how many successes I want. So for our example that we're dealing with, N was 5 kids, success is 0.25, I want to know 2 kids. So 5, comma, 0.25, comma, we want to know 2. Oops, got to get the comma there. And again, we arrive at that same value. Now, if I go back to this one just quickly, this is cumulative. Okay. So cumulative CDF, which if you recognize was letter B, okay, or binomial CDF, is there. What that does though, it's going to add the values from 0 to X. So what we got to be careful of, if I did choose to use this, again it's B, so I'm going to go alpha, B is your apps button there. Okay, I can do the situation 5, comma, 0.25, we enter the same things in. Now, you got to be careful, because if we just say 3, what this is going to do, if I plug in 3, it's going to add up x equals 0, x equals 1, x equals 2, x equals 3. So if I do that, what we have to recognize is, hey, I don't want those. So then we got to come in and subtract it from them to get our probability. So there'll be some times when we need to, they had said greater than or equal to 3, then what we have to do is cut this off, and the next value I would use is 2. One of the things they talk about if on the exams, if you write down or if you're asked to find binomial probabilities, writing just this piece down is not enough. Okay. You have to indicate which each of those numbers are. You have to talk about how 5 or my N is the number of trials I have. The 0.25 is my probability of success. 3 is the number of successes I'm looking for. All right, a couple things that will happen, and I'm just going to touch on these quickly, when I put together a histogram for my binomial distributions. If I have a probability of about 0.5, I'm going to have a symmetric distribution. We'll talk about this a little bit in the next one when we get into mean and standard deviation. So, but then when I have a lower probability, okay, it's going to be skewed to the right. When I have a high probability, it's going to be skewed to the left. Reason being, low probability, okay, likely that we're not going to have a lot of successes. High probability, we probably will have a lot of successes. We're more likely to have more successes.